Smooth. Yeah, hi everyone. Thanks for the intro. So, yeah, we've been working on this since 1.5 years, and it's it's kind of related to the two talks before, but I think there's a large chunk in this talk that um, is about like extending circuit DSL into something that covers more. And so I think I'm going to focus a bit on that because it's um, kind of a new thing. So that's why it's called from verified circuits to verified zkVMs. So here's the hello world of a circuit DSL. The is0. So this is clean in a nutshell. It's embedded DSL for ZK circuits that are verified. So there was this idea from the start that we want to. It should not be like a verification pipeline, but it should be a circuit front end. So I wanted it to look nice as a circuit front end, and it should also kind of force you into verifying your circuits correct. So it's like that's why we bundle everything together. There's with every formal circuit, you have like the circuit here, and then you have your soundness and completeness to fill in at the bottom. So it's the state monad kind of circuit DSL, I would say. As you maybe see, then it gives you these like what was called a post condition before. You fill out a spec. There's also a precondition that you don't have to use, and then yeah, and then we also have a bunch of automation to make these like easy to prove. So a core tenet that I had is that if your circuit is simple or trivial, or the statement that you prove is trivial, then the proof should be trivial. It should, like, also you expressed, Marco, that you shouldn't have to worry about the boilerplate of the state monad or something. You should just be thrown into your mathematical statement, and if the mathematical statement is easy, then grind will get rid of it. So that happens in these proofs. Yeah. So maybe I'll also give some history on where I'm coming from and why this project looks like it does. So I've been working on sort of circuit DSLs for 5 years, I think. So I've been working on something called O1JS for over 3 years. Put a lot of energy in that. So at that point, I also already had a lot of like hard-won experience, and I really liked this project. So if you're, I think we see this in our ecosystem as well, that if you invest a bunch of energy in some ecosystem, then it's kind of weird to start something completely new. So for me, this was like when I started this, another circuit DSL, it was kind of clear that this would be my last one, you know? Because, yeah, I'm not going to start from scratch another time, so this one kind of has to be perfect for me. These things that I put on this slide, they represent pretty strong opinions that I have about what it is required to be perfect for this circuit framework. So I put two chilies there for two parts that are different from my previous talks. But yeah, we all agree that it should like look nice. That's one thing I gained over TypeScript. Now in Lean, it looks like mathematics. I can do plus and not dot add something. Much better. It should have good PX, proving experience. What we saw before, like a nice tactic. Yeah. Thanks. Is it better? Okay. So I very much strongly believe that what I build has to be low level, and it has to talk about constraints, and it has to give you a witness command and so on. It definitely not going to be compiled. I think, but that's just a different I think use case for circuit DSL. So it's my thinking is that for many programs you want a compiler to not think about like assembly at a low level. Circuit is kind of an assembly, but for very precious programs, the assembly is really you want to be able to program in assembly, and because it has to be as efficient as possible, and yeah, you know. And I just want to target that direction. I want to target a zkVM that's implementing core infra, and they will write their circuits by hand, and they will not use a compiler to create a compiler, so to speak. So then the next thing we kind of all agreed on, I think, it should be like general purpose. That's why we write it in Lean. That's why it's not circom, where you're passing three-dimensional vectors of signals from the very starting point through to all the circuits. It should give you nice abstraction capabilities. You should be able to define higher level types that are kind of circuit types and so on. So, and you should be able to define loops and so on. You should be able to use the full power of Lean to write your circuit builder. And then the other chili is that it should definitely model completeness, and it should have proof of computation, so which is different from zk-Lean, I guess. Yeah. Because we'll come to that later. So and the non-goal is that it kind of abstracts circuits away and make them look like normal programs, because circuits are an interesting model that I want to preserve. Okay, so that was the part about connecting to the other projects, I guess. Now I want to describe roughly the basics of Clean to prepare you for the rest. So, but I will keep it short. So a circuit is a function from this number, doesn't matter too much at the moment, to like basically a list of operations. So it's basically a circuit is a list of operations, and an operation is either a witnessing operation or an assertion, like that's the equal constraint, or a channel interaction, or a subcircuit. And a subcircuit is actually just again a list of these three. So it can be nested, and nesting was important for scalability, basically, so that we can compose circuits and not reason about the whole deeply nested thing every time, but kind of stop at the subcircuits. And then, for example, we can define what constraints mean for each one of these these expressions. We have that the expression evaluates to 0, so it's a zero check. That's what it means that the constraints hold. All right. Maybe I can have some water. Yeah. Okay, thanks. Thanks. Soundness and completeness is not surprising. We have sort of preconditions, then we assume that the constraints hold, and then it follows that the postconditions hold, and this is very rough, but importantly, the assumptions and the spec are about the inputs and outputs of a circuit, and the constraints are about everything in between. So we kind of want to abstract away, looking from the outside, we want to abstract away all the things that happened inside a subcircuit. We only want to talk about inputs and outputs. Yeah. Okay, now when we started out, we basically had plain constraints, what we saw before, and we had a sort of we wanted to model lookup tables as well because all of the real circuits use them. So we had some weird lookup operation as well, but it wasn't very nice, and we wanted to model it properly, the whole concept, and that's what this talk is really about. So we started thinking about what's the common abstraction or the best way to represent all of these different multi-set equality arguments in a circuit DSL, which should cover things like lookups, the Planck permutation argument, and also all kinds of cross-table interactions in zkVMs. So maybe prior work or where this comes from. So there's this concept of there's kind of an architecture for zkVM that the industry kind of landed on. There are similar across different projects. So in Cairo, for example, like in Starkware, they call it flat air. In Binius, they used to call it M3. OpenVM calls it air with interactions. So the concept is you have different tables. We call them components. And these tables, they basically use one row constraints. So the old VMs, they used like adjacent row constraints every time. But nowadays, we have a circuit on every row. And the only way that two rows communicate with each other is with channels, with these multi-set relations. So channels mediate both between rows of one table and between different tables. And then there's a sort of channel balance that is proved as part of the proof system. So we prove for every channel that all the elements added to it cancel out. So it's a multi-set zero check. And also interestingly, typically a zkVM like that has there's a channel that becomes a central point of the whole system. So we used to have VMs where there was a CPU table, and that was like the core, the central point. And the CPU table used other tables to spawn out computation. But the whole trace was in the CPU table. And nowadays, we have multiple tables that share the trace, and the thing that holds it together is the state channel, the VM channel. So we have like the add instruction will have its own table, and the multiply instruction will have its own table, and they will both pull from the state channel, perform a transition. The add table will perform an addition. Depending on the opcode, we will use a different table to perform a transition, and they will push back to the channel their result. So that's kind of, it seems to be more efficient that way, I guess. How am I on time? This was about a third, maybe. So yeah, I prepared like I worked for a couple of weeks or even months on an example that I tried to make like a toy example, but still representing the whole thing I want to model in its generality, and that was this Fibonacci example. So just to recap, I want to show you the components of it. So we have 3 tables. One is like a classical lookup table, which has bytes in it. It's a range check table where you can check that your element is a byte. Then we have an addition table. So this is Fibonacci on 8-bit numbers, and it stays in 8-bit numbers, 8-bit Fibonacci. Okay. So there's an addition table which pulls an element from the bytes channel, which means this is a byte, which will be the result. and then it will constrain this result of the addition to be the sum of two of its other inputs, the sum modulo bytes, and then it will push, it will emit to this addition channel. So there's one table, there's one channel that's consumed, the bytes channel, and there's one channel that's the output of this, the addition channel, kinda. And then there's the Fibonacci table, which is sort of like the VM here. It performs a state transition. It pulls from the Fibonacci state channel, performs an addition by also pulling from the addition channel and pushing to the Fibonacci channel again. Is that kind of clear? So these yellow boxes is what we would call the component or table, and the blue things are channels. And yeah, there's sort of a hierarchy here, and there's a main channel, the Fibonacci channel, and these are the ingredients, I think, that we find in zkVMs basically. There's light generalizations of this, but this already gives you a good implementation of a zkVM. And then, I should not forget then, there's like a public input and public output to the whole system. And in this system, that's typically like an initial push that you perform to the VM channel and a final pull. So you push like the beginning state that might be a constant, like your constant, like 0, 1 Fibonacci starting state, and at the end you pull out the final result of the whole computation. That's like your public output. So the problem with modeling channels in a circuit DSL is that your soundness of your we have three circuits here, right? We want to treat these like little things that are self-contained. Like the addition shouldn't really know about this whole zkVM structure. It should be just an addition gadget. But it needs this property that this output value is a byte. It needs the range check to prove its own soundness. So it relies on something that cannot be checked by local constraints, because ultimately the fact that this output is a byte comes from some global multiset check, which we can't nicely represent in this local circuit. That's a problem. So we want to, I'll keep it at that. So a first obvious attempt is that we just associate some property with a channel. We just have this structured channel, and we define this function from, it has some type, some message type, and then we define an arbitrary property that is the guarantees that you get when you take something from the channel. Yeah. So for the bytes channel, this would be that the message is on a field element that's smaller than 256. So there's an arbitrary property, and then in your soundness proof, you just use this new statement, where in addition to your constraints, you also assume all the guarantees from for all the pulls you did for any channel. Okay, and that's basically what our initial lookup operation was. Just kind of get it working, you know? But I wasn't really happy with that, because this guarantees property can be anything. It's not anchored in anything else. So, for example, I have this. I could define this very dump channel, which has the property false as its guarantees. So every time you pull from the channel, you obtain the property false. And so you you can define a false circuit where the constraints of the circuit imply the statement false, which is sort of frustrating. right? And it's sound, you know, according to our definition of soundness, this is easily proven to be sound because it assumed the false statement. So not happy with this. So it would be better if we at least model both sides. If you pull, you get the guarantees, but if you push to a channel, you have to provide the guarantees, right? You have to, if you push to the false channel, you have to prove false, okay? So you can't really push to it. That kind of gets us towards modeling the whole system, where some tables will push to some channel and other tables will pull from it. And then there's this grand vision, of course. So now we want to write many gadgets that maybe some of them pull and use this, some of them push, and then we want to combine them into an ensemble of which is an air or a multi-air, a flat air, and then once we have assembled everything in the right way, I want us to get rid of all the assumptions that we made and actually prove a real soundness theorem. So we want to prove global soundness, which when you have the assumptions that all the tables need and the constraints that all the tables produce, then you add an additional, basically a global constraint, the channel balance for all your channels. Then you can directly prove the spec. You no longer have these ugly guarantees. So the guarantees were kind of just a little helper device to get you there. It's like sometimes when you prove an induction, sometimes when you prove a statement by induction, you make the induction hypothesis stronger than the output because it kind of smoothens the way to proving the output. And that's very similar, I think. So with this setup, if you can prove this, then your guarantees can actually be anything. There are no restrictions as long as they help you prove the local circuits. And since you get rid of them in the end, they don't hurt you, right? So how did this work out? Why should this be true? So channel balance means that for every pull you do, there has to be a push. Otherwise, you wouldn't have balance. No? If you would only pull from a channel, then it would just be all multiplicities minus 1. So our balance condition actually has an extra condition that the number of interactions are smaller than the field size. So it can't, with a lot of minus 1 multiplicities, you can't underflow. So balance actually is structured so that it implies that for every pull, there must be some push somewhere else. So for that push, we had to prove the guarantees. And so that's why we also have the guarantees for the pull, because they're the same message, so it's the same statement, right? What can go wrong? Okay. Well, we had these guarantees of the push came from somewhere. They came from another circuit, but that circuit also had some assumptions that it made from some other pull that it did, probably. So it's not that simple. There are simple cases, though. There are cases where we have a strict hierarchy of channels. You know, the first channel doesn't pull from anything. So that's already the next slide, a simple case. We have a list of tables in some order. We have to say what the order is. And we require that for every channel, or for any channel that participates in this argument at least, the tables that push to the channel have to come before, and then the tables that pull from the channel have to become after. And no single table can obviously pull and push to the same channel. So that gives us kind of a way to prove this thing by induction, because the first table is like a base case. It cannot pull from anything. So its pushes are unconditionally carry their guarantees. And so in the Fibonacci example, we kind of have a partial hierarchy. The bytes table pushes to the bytes channel. the add table. So from that on, the bytes channel is no longer pushed to, only pulled from. Then the add table pulls from the bytes table and pushes to the add channel, and from that on, the add channel is no longer pushed to. Okay, so these channels are done, and now any table can pull from these channels, and it's fine. And we proved this, we formulated this ordering in a way that can be easy to prove, like for the user. And that's what we call is sound channels. And then the theorem is that the interesting soundness theorem, which is table soundness, follows from sound channels. Which means that all the guarantees for these channels, even in the Fibonacci table, we can deduce that all the guarantees for these channels are satisfied, even though the Fibonacci table doesn't fit fully the hierarchy. So now there's the harder case. What do we do here? So we have these nasty VM channels that are pulled and pushed to from the same table. So you can't always prove what we want. What do you mean by that? So I thought, I didn't think about this too hard from the beginning. So I thought I would prove this table soundness for every table, for every channel. We will prove that all the guarantees hold, but that's not the case in general. So in a VM we can actually, there are many VMs that support transitions that loop. Like one transition, there's a couple of transitions that end up where they started. You want that if you have a real VM, you want to have the capability for infinite loops. And so you have closed cycles, and if you get a proof of a VM trace execution, in practice it can contain such cycles that that's not ruled out by any of the proof systems that I've seen. And in these cycles, you have the guarantees. They form a cycle of implications. There's no base case where you know the guarantees actually hold. One transition assumes some guarantees and proves some other ones, and it goes around. But in general, we don't know that any of these hold. So that was disappointing to learn. Yuichi kind of immediately noticed that and pointed me to this, that yeah, there can be cycles. What do I do about this? Yeah, it's sad. So, but in fact, it's not that bad. If you try some time, you prove what you need. Because in the end, we don't care about the cycles. We just have to formulate the soundness statement in a way that we care about it. So the public input and output of a VM is this initial pull and final push, the other way around, sorry. And they can't be in a closed cycle for reasons. Okay, so because if the final pull was part of such a infinite loop, the balance doesn't work out. There would be a loose end. So from the construction of the thing, you know that the initial and final thing are actually part of the same path that has a beginning and an end. And it's a nice soundness statement to say that if you assume the guarantees of the initial push, it follows the guarantees of the final pull, right? So that's basically, typically this, the guarantees are there exists a VM trace that leads to this state. And this is what we understand as soundness for a VM. We get the statement, there exists a valid trace from the initial to the final state. Okay, so the proof actually goes through, and I have this is a pretty long proof. I have a nice argument in Lean for this, which doesn't talk about cycles at all. It's just an induction that just works. Maybe I can show you that later. How are we in time?
Coffee break is in 20 minutes, so you have.
Cool. Yeah. So, without further ado, here's basically my main result. Assume I already defined these Fibonacci components, and I proved them sound, and it's not very hard. Then everything I have to do in addition to prove the end-to-end soundness property that I promised is these 10 lines of Lean. So that's because the things we assume about the things we have to assume about these components are very simple properties, like you don't pull from that channel, or you don't push to this channel, or in the case of VMs, we have to know that all the pulls and pushes are -1 or +1. Or no, that's exactly 1, -1, and 1, +1. So it's all it's all just simple properties of the channels, how these channels are used. So all of these just proof by simp, and here you see two of these proofs in one line, and here you see 2 proofs, and here you see more, and they are all about using our simp set, our custom simp set, which is called circuit norm, and then unfolding definitions in addition to that. That's how it's supposed to be, I think. And if you're at that stage, you could actually write some automation to just unfold the definitions and just get rid of the proofs altogether, of course. That's just an exercise. So you don't have to do any proofs on top of your local circuit proofs. Just combine them in the right way. And combining in the right way, I mean, it's here. So we add, I mean, that's the main thing. We add the tables in the right order. We add first the bytes table. Then we say, okay, now this channel is finished. We add another table. We say then this channel is finished. We kind of tell it the right hierarchy at the beginning, and at the end there's the grand last step where we add all the VM tables at once. And that works on top of the existing hierarchy. Yeah. Cool. Where am I? Okay, this is. Yeah, maybe just to show you how kind of the final thing looks like. So this is kind of the main theorem of the. So this is where I did this was of combining all the components, and then just to prove that this is actually an interesting statement, I wrote it out here concretely. So if I take this Fibonacci ensemble and assume the statement, so the statement is kind of what the ZKProof is supposed to give you, like it's the channel balance and the constraints. So let's look at the statement to be convinced this is not some garbage. Statement for an ensemble is there exists a witness, so that the public input of the witness is what goes in, and the constraints hold and the balance channels. Probably. Okay. I don't know if that was convincing. And then if you assume the statement about this number n, x, and y, then essentially x and y are the output of Fibonacci. So it's a bit ugly because I have to avoid the overflow, kind of avoid the overflow here. So that's for me to fix. It needs more theory in this framework, kind of. But yeah, we actually can directly prove the interesting relation from the statement. So that's cool. So a little interesting after observation. Why is completeness also important? So yeah, I should show you this in code. So let's go back to this grand construction that I was so proud of. So we would expect that. I mean, what if I comment out the bytes channel, the bytes table? It works. It's still sound. If I also remove the addition table, it's also sound. So interestingly, kind of the assumptions that the Fibonacci table does, they come out of nowhere in this case, sort of. Why? Because the fact that there are tables that fill these channels, this is a completeness property, not a soundness property. Okay, so in this case, we just have a meaningless channel balance condition. The channel balance could never be satisfied with this setup because there's no table that pushes 2 bytes. So okay, if you have a trivially false assumption, the channel balance, we can prove whatever we want, obviously. So kind of unexpected. For demonstration's sake, I also proved the false circuit that I showed before to be part of a sound ensemble. So for the same reason, because you just can't push to this channel, so you just can't have channel balance. So I motivated my whole talk with the fact that we don't want to have these stupid circuits, but in fact these are still sound end-to-end systems, just not complete. And that's why proving completeness is a very good idea to avoid meaningless soundness proofs. All right. Okay, that was.
Thanks for talking about this topic. I met this at Maiden. They called them buses. I think it's a good name, but yeah. I mean, it's exactly what you. And I was really learning about this, and I was a bit puzzled that you can push, but actually you can pull before you push, and so it's a bit unintuitive. This is what you when things are to be pushed before being pulled, that was a simplification that then it was lifted later, right?
I mean, there are basically 2 different soundness arguments that I established for 2 different cases that are just disjoint. The VM case was it had assumptions that the lookup table case didn't have to make, and the lookup table case had assumptions that the VM case didn't have to make. So so it's a bit abstract without seeing all the theorems, but this case of doing both pushes and pulls, it works under the condition that it's just one pull and one push.
Sure, that they need to add up at the end. Okay.
Yeah.
Okay. And so the other thing is, so does this become a sort of trace property in the sense that you need to unroll the whole thing before you know if, so that it sort of removes a little bit of the local reasoning that you can do, right? The fact that at some point, I don't know if up to here we're good, because maybe I'm pulling something that somebody's going to push later. So unless you unroll all the trace, like you can never be sure if everything is okay. Was this a problem, or is just?
Yeah. I mean, this kind of permeated through all my work. For example, I introduced a relaxation of this balanced channel assumption, which is to say the channel is balanced if we assume that there are more elements coming in later that have where we already assume their guarantees. So it's kind of like conducive to this sort of induction.
Okay.
Yeah.
Thanks.
Any other final questions? Okay, coffee break. Thank you, Gregor. And then we'll be back after the coffee break. And then we'll also talk about AI.